So, hello everybody, and today we will have our first practical exercise for which you will need to make a report. Yes, we can register after the class. So, in order to system, I have provided for you this description of the tasks which we are going to do, of some individual parameters that each of you is having. So essentially, each of you is this time having different signal and the sampling time interval, as well as what needs to be put inside of the report. Finally, there are some additional guidelines explaining certain stuffs and showing some examples what we should expect for your reference. So this practical exercise is about sampling and discrete Fourier transform. Well, in this exercise, we will not write our own Fourier transform. We will use FFT algorithm to get the job done. And basically what we want to study here is how exactly the sampling procedure affects your ability to reconstruct a signal after it has been sampled. So here, for example, you see in the blue line is your continuous signal, the analog version of it, and in the red samples are the discrete values of the signal. And the question is, can you again recover these red samples back all the way into this blue line, and how exactly, how you could put it, how exactly accurate that reconstruction would be? Is it going to be perfect? Is it going to have any differences? Will it be possible at all? As we discussed, that exactly depends on how often you are going to take these samples. So that's what we are going to try out in this exercise to see how the sampling interval affects your ability to recover signal. And at the same time, we'll see what happens with the spectrum, which we will get by using FFT function. So each of you has a different signal, which is specified for you in the OR2 system as well. Also, pay attention that here I have added the link where you actually can upload your PDF report for this exercise. So the deadline for reports is the semester end. Yes, so you can do them until the end of semester if you need to. And here is the folder with these individual signal text files. So I'm going to download signal number 21 for me, and you should download whichever is specified for you in these guidelines. Yes. So in my case, I will use this one. Now we may open it just to check what's inside. And inside you can see is just a column of numbers, specifically 320 numbers, yes, which is my signal. We'll consider this signal to be a more sampled version, like an analog in simulation for us, which we will take readings from. Yes, so that is basically our analog base, which we are going to consider as a signal, and accordingly work with that. So I'm going to actually start the MATLAB. You can do the same work in the Octave if necessary, yes, or in MATLAB Online, Octave Online probably also, but you may need to load some additional package if you use that. So let me actually copy this file I have downloaded into my working directory. So now when I create new script called practical exercise 1, let's say PE01 sampling DFT, for example, you need to make sure that this signal file is in the same folder with your script that you are going to run. Because if it's not, then it cannot find it. So what we are going to do now is to load this signal in this MATLAB so that we don't have to, copy that long column of numbers to actually do that. It's completely possible and actually quite easy to do. So let us begin working our code. As usually, I recommend cleaning everything up. In some situations, we don't want to do this, but when you start a new code, there is no reason not to, because if I run it, then I will have in this workspace some results which I don't want maybe. So let's specify input parameters, such as sampling time. So that will be TS. In my situation, let it be 1 millisecond. Again, for your reference, you need to check what is sampling time specified in this column for you. So I will use 1 millisecond. And you need to use whichever is specified for you. So this is sampling time interval. There is one more parameter which we will change, which makes sense to specify, is called sampling ratio, or rather downsampling ratio, 5, 10, or 20. So let's start with number 5, and samples is going to be 5. So that is downsampling ratio. So what that means is that out of the signal which you are going to read, we are only going to keep every fifth sample. Yes, so we skip 4 samples, we save fifth. We skip 4 samples, we save 10th, and so forth. So we only save every fifth sample in our signal by running a sampling procedure like so. Now, accordingly, we are going to read the signal values from a text file. For that, we will use a function called load, yes, and this function saves the result as a variable inside of MATLAB memory. So we'll run load, and in brackets you need to specify the path and the file name. In my particular case, I already am in the same folder, yeah, so I only need to specify signal21.txt. Although sometimes you may need to specify the path as well, which is then specified like, well, somehow, yes, like for example C users and so forth and so forth. Yes, so in this particular case it's not necessary. Yes, if you put it in the same folder as your script, which is here my script file, here is my text file, then you can refer to it with just its file name. And that does it. Yes, that actually loads this file, and you can work with that. Now, I am going to need to know how many samples are there in that file. So I am going to read that by running length command. So find out number of samples in file. So if I run it, you will see now that here I have new variables like n, 320, that's how many samples are there, and s, that is my downsampling ratio 5, signal itself, which is a vector of 320 elements, and time sampling interval, which is 1 millisecond. Yes, so with that in mind, now I can actually display this signal to decide what and how I'm going to do with it next. Before that, however, we want to say specifically, we didn't specify this sampling interval of 1 millisecond for nothing. That's actually the time interval between these 2 points. Yes, so if you open the signal here, you see that there is a value 8.1 something else. Yes, then 1 millisecond passes, you get next value, 1 millisecond, 1 millisecond, and so forth. So you get to display a new value every 1 millisecond, or 5 milliseconds, or 2 milliseconds. So we want to actually, in our plot, to show this signal as a time function. For that, first we then need to specify a time vector matching this signal. So specify time vector to match a signal loaded from a file. Now, these guidelines actually do provide some extra explanation for you as well. Yes, like what exactly we are doing. To put it short, the idea is quite simple. We basically first say that we specify this range as numbers, first, second, third, and so on. And then we say, okay, now each of them is actually having this sample time interval. So let's do it in two steps. First is to specify this as samples. Well, actually, let me call it as n to avoid confusion. So this is sample numbers, like 0 sample first, second, third, and so on. Now I know for certain that between two samples there is a time duration of ts, 1 millisecond. So I can easily convert that into time by multiplying with this value. So now it is a time vector in seconds. So now we have x-axis time, y-axis these signal values, and nothing really prevents us from displaying this analog in quotes signal. Analog in quotes because it's actually still a digital signal. And you can even see that this is a text file on the hard disk, yes? That's a digital information. However, it's so often sampled that it makes an illusion of looking like an analog in our screen. Yes, so we will consider for simplicity of our experiment that this is an analog signal, which we then are going to sample and convert into discrete signal. So display a plot of analog in quotes signal. For this, we are going to use a plot function just like we did in warm-up exercise. However, first I'd like to say that we are going to have multiple pictures in this exercise. We are going to have picture of signal, its samples, we're going to have picture of spectrums for this signal, and finally one more picture when you will compare original signal and recovered version of this signal. So it makes sense to actually organize this somehow by separating these figures. Now this is going to be figure 1, which is going to show us time domain signals, that is original and sampled version. And then we write the plot function. So x-axis is t, time, y-axis is signal, s, and any additional parameters like color or let's say line width, for example, can be specified here also. I usually prefer to use grid on, although it's not mandatory. And we will also assign the labels, like X label is time in seconds, and Y label is a signal. So with this construction, we can actually create a picture of our signal, a plot. So let me run it to show it. Here you can see this signal that I am using. Now, I already taken care of some necessary steps for you, such as aliasing filtering and generating it. So in essence, I run the random number generator to generate this as a random signal consisting of multiple components. But then I did some extra filtering to make sure that with appropriate sampling time interval, it's going to be possible to recover it perfectly. Yes, so for each of you, this signal is going to look slightly different. Yes, but more or less the idea is the same. Also on the x-axis, we can see now that the total signal duration is a little bit over, well, actually I can say specifically it's like 320 milliseconds, yes, so 0.32 seconds. That is number of samples multiplied by the interval between them. Again, for you this number might be different depending on what is your sample time interval. It can be 0.6 something, it can be actually even 5 times more, like 1.5 something. Yes, so again, depending on your sampling time interval. What we are going to do now is to take readings from this signal as samples. So you can move this cursor, yes, and read specific points, and you will see that actually it's consisting of points. It's also digital, but these points are so often enough to make an illusion of a smooth line. It's okay. For our experiment, we need some assumptions about what we consider analog signal, what we consider discrete signal. Now we are going to make sampling of this signal to make the discrete version of it. So that's actually, let's try maybe follow up. What we did here was task 1 so far, yes. Load this signal, it will be considered like this. And then in task 2 we will do sampling. So let's say that this is the task 1. You can actually organize in MATLAB in something called like cells, like running separate cells, yes? Run section. You can only run this section, only run this section, and so forth. And it's a little bit easier to organize it this way, yes? So task 1, load and display analog signal. Well, analog is in quotes because it's actually this digital one, discrete, but we consider it to be an analog in this example. So task 2 now will focus on sampling the signal, and display discrete signal. So basically we sample the analog signal and we get a discrete signal. So we are going to do this sampling by simply skipping 4 points out of 5. So we skip 4 points, we keep 1 point, skip 4 points, keep 1 point. Well, specifically we skip ns minus 1 points because we later are going to change that. But that's actually quite simple to do. Let's switch to the console so to show some examples. Say I have numbers from 1 to 10. And what if now I want to skip every 2 of them and accordingly have sequence like 1, 4, 7, and 10. You can do so by specifying a step of what you want to skip. So my step is now 3 because I want to skip 2 numbers and keep every third. Yes? So this way I actually can downsample this sequence to whatever I want to. I can actually downsample it with some 5 or 4 and so forth. Yes? So basically that's going to be the same approach. Now, this is useful for us because what we want to do this downsampling for is the number of the sample which we are going to have. So we are going to use these numbers as indexes of an array. Yes, so basically that's going to be array, our signal S, and our addresses which we read are going to be specified by this downsampled version. So what I'm going to have now is from 1 with a step of ns all the way up to n, which are these samples of the signal S that I am going to keep. All the others will be gone. And you can do so by simply saying, okay, I will use this as an addresses. Yes, so it's going to display only those samples. So we want to save this as an as discrete 1 with ns to n. That's actually downsampling because in reality the signal is also discrete. So we downsample one discrete signal to get another discrete signal. Although now one of them looks like an analog signal, the second one will start looking like a digital one, or discrete one rather than this in this situation. So that's downsampling with a factor of ns. The same procedure actually needs to be done also for our time vector. Time discrete is going to be from 1 to ns to n to match these time points, time stamps where we have each sample. So downsampling time vector to match time stamps. Finally, the number of samples we are going to have is going to be reduced by 5 times. So we had 320 samples, now we'll have 64 samples. So that might be a good idea to actually have this number of discrete samples, like length as the number of discrete signal samples. So what we want to do now is to display on top of this continuous line these samples to get two pictures on top one of another like so. So you have a continuous line and samples, yes? Now you can do that by specifying next plot. So display discrete signal plot. Now, first of all, we want to stick to figure 1. Well, we didn't switch figure 1 yet, so I don't have to type it again, because it's still going to do anything you are going to do, it's still going to happen to figure 1. But in case you were switching that, you would have to switch to one you want to work with, yes? Which makes sense. If you have multiple figures, you won't specifically display that in the figure 1. Just to avoid confusion, I'm going to use it anyway, although not necessary in this case. Now, if I want to display a stem function, I can run this as a function stem, discrete time vector, discrete signal vector, and the color is going to be red. So if I run it like so, what is going to happen, my line signal is going to disappear because I didn't say I want to keep it. So to avoid that from happening, I'm going to have a hold on before displaying a next plot and hold off after it. So this way, the existing plot is going to be frozen, it's going to freeze, and on top of that, you are going to display next plot. So then it's going to look like this. Now you can see we have red samples from our discrete signal, and accordingly, what we want to know now is it possible to recover our original signal from these samples? Now, before that, however, let's also add a legend saying which line is which. That's actually quite simple thing to do. You only specify a legend command, and inside of that legend command, you specify two text strings. One is going to be for the signal you draw first, that's going to be our analog signal, and second is going to be for the next. So these entries needs to be specified in the same order as you were plotting them. So this was analog signal, this is now discrete signal. So now you have a legend. If you want to, you can also add title, change colors, format, and so forth. As we'll go further in this course, we are going to some more advanced stuff to these plots. But for now, these plots seem to be good as it is. So let me move it around a little bit and let's go to the task 3. Task 3 is now display spectrums of A, analog, B, discrete signals. So what we want to do now is to display what happened to the spectrum of your signal after you did sampling to it. Because as we know, the spectrum is kind of like unique description of your signal. So meaning that if your spectrum changed, then the signal also had to change. Yes, that works exactly like that. Now, here in guidelines, here, you can see some instructions how to calculate that. Yes, so we discussed in the lecture that we need to calculate discrete Fourier transform, and that there exists a fast Fourier transform function which is as simple as to simply say FFT of the signal you want to calculate, and here is your spectrum. Now, we did mention on the lecture that you have to have a power of 2 of the signal values. However, here you see that we don't. It's 320, and okay, here we do, it's 64 in this particular case, yes. But nonetheless, it's going to work because, as I explained, FFT, well, LEAP FFTV, which is created by MIT, actually first checks what is the number of your samples, and then depending on it, it can actually use different algorithms. Yes, so it's kind of like if condition at the beginning, and there are actually optimized versions for each possible scenario. So even if it's not power of 2, it's going to pick whatever is fastest method to do the job done. And if it is 64, for example, yes, then it's actually going to use the real FFT algorithm. So it shouldn't bother us. So far, what you want to understand is that it can work with any number of samples. It doesn't have to be a power of 2 because it's having multiple variations of implementation, yes? But the true, real FFT algorithm actually works only for powers of 2. Well, you can think of it as you are actually going to get speed increase in that case only. So, okay, let's calculate two spectrums. One is going to be FFT of signal S, which we normalize with number of samples divided by n. As you recall in lecture, we had this. We can actually even go here and check the slides. In formula, here it is, 1 versus n, because MATLAB FFT calculates only this part without 1 divided by n. So we have to add that manually. Then we do same stuff for discrete signal, FFT of S discrete versus n discrete. And that is it. We have calculated two spectrums, one for original signal, one for sampled version of this signal. So let's add comments like saying original signal spectrum, and this is the sampled signal spectrum. So we want now to display them both, but in task guidelines, we were specifically asked to display them in a new window, yes, by using a subplot one beneath another. So we want to be able to see them both, but in different pictures so that they do not mix. Yes, so we'll use subplot for that. Before that, however, we need to specify what is on your frequency axis W. Yes, because frequency, the spectrum is calculated over frequency, not over time. Now, from theory, yes, from theory, we do know that whenever you have sampling signal, let me actually have this as lines, then we have some spectrum, well, let's say we have rectangular shaped signal pulses, so that for your discrete version of the signal, we are going to have this extra mirrored version of the same part of spectrum, like so. And we know for certain that this frequency, where is the last sample, is actually our sampling frequency. Whereas here in the middle, where that happens, is f sampling divided by 2. So the half of the sampling frequency is where we have these maximum components, after which we start focusing. So obviously the first frequency we work with also is 0. So our frequency range is from 0 to f sampling. So the first result of this FFT, S1, is corresponding to 0, and the last one is corresponding to f sampling. So let me add some comment here explaining that. Like S1 matches the 0, and Sn matches f sampling. So anything in between is then evenly distributed into steps. So therefore, a step is f sampling versus n. So each of these samples then is, over the distance of f sampling versus n. So for example, here is f sampling versus n. And that means all that we have to do is basically define a range from 0 to n divided by n, so that's from 0 to 1, and multiply with this step. So let's construct this frequency range. Define frequency vectors for spectrums. F sampling itself is sampling frequency. That's the number of samples you take per 1 second, which is inverse of the one sample duration. Obviously, if you have a sample of 1 millisecond, then you will have 1,000 of them in 1 second, like 1 versus 1 millisecond. Yes, that is also converting seconds into hertz. That is second, 1 versus second. Yes, time units into frequency units. So now we can specify the frequency range like from 0 to n minus 1. So actually we start counting at 0 and we have a total of n samples, so we have to stop at n minus 1, which we are then going to normalize by n minus 1. Well, actually not n minus 1, by n, sorry. That's actually to make the last frequency to be the sampling frequency, which is not included here itself. So we are in range from 0 to 1, almost 1 now, and all you have to do is to multiply that number with f sampling. Yes, because this way you are going to automatically achieve that your last position is almost f sampling. Your next position would be f sampling, but that's where the spectrum starts periodically to replicate, which we don't display. Same we need to do for the discrete signal as well. Now, that is for analog signal. For analog signal, well, analog in quotes again, because it's actually a digital signal, but comparative to our discrete signal, it can be considered as continuous function. For discrete signal, the sampling frequency of discrete, well, as it turns out, from downsampling definition, downsampling literally means reducing sampling frequency by n times. So that means your original sampling frequency fs gets decreased by ns times. So it is as simple as that. Downsampling is reducing fs by ns times. And discrete frequency vector is specified just like that as well. 0 to n d minus 1 versus n d multiplied by fds. That's for a discrete signal. Now we have spectrums themselves as a complex numbers. Don't forget that these are calculated for exponential, complex exponential, so therefore this result is actually a complex number, and we also have this frequency range for which to display this spectrum. So let us now put everything together and display a plot. So display a new figure with two spectrums, one under another. Yes, so basically two of them not in the same picture but in separate ones. So first of all, I'm going to call figure 2, switch to new figure, so that my old one, its size, position, and all of that doesn't get reset. Because of that, I'm going to change it. And accordingly, in that second figure, I'm going to use something called a subplot. So let's try subplot 2, 1, 1. So that stands for two pictures in one in the, well, okay, let's say like this, 2 rows of pictures, 1 column, and picture number 1. So essentially what we have here is a matrix of pictures with 2 rows, 1 column, and currently we are working on a picture number 1, which is going to be a stem because this spectrum is also a discrete process. Yes, so for discrete signal, you with discrete Fourier transform, you are going to get a discrete signal. So for discrete we use stem, for continuous we use plot. Now, x-axis has frequency, y-axis has absolute value of the spectrum. Now grid on, x label frequency in hertz, y label is the spectrum. Actually, let me also add title saying that this is analog signal. Then I'm going to display the second plot. Subplot. Well, actually, let me run it just to show how it's going to look like. So now you see I have created a new figure, and inside of that figure I only use the first part of this subplot. That's defined by subplot 211. So it splits this window into 2 parts, vertically actually. That's number of rows. If I were, for example, to specify this opposite way, like 1, 2, 1, then it would split it vertically, like this, yes? I can even combine it, so to have 4 pictures in total, yes? So this way you can actually design however you like to see it. But for this particular case, I prefer to see it more in this length, let's say so, yes? And here you see the spectrum of discrete process that actually repeats itself after the frequency of 500 hertz, yes? So it's a mirrored copy of itself after this frequency. Now, we can clearly see that having the 500 sampling frequency is good enough because there is no spectrum part left after 500 frequency. That is because I did some filtering for you in advance to make sure that there will be nothing left, yes? Because normally, if you get some signal, you are supposed to filter it first, but we'll discuss filters in this course later. Then you can start reading its samples, yes? Now, to skip that part, which you are not currently maybe ready yet for, but will be, I have done this filtering for all of your signals in advance. So what we want to do now then is to display the second plot, subplot 212. That's the second plot. So picture number 2. So that's the last one of this, which we also use stem for f discrete, absolute value of s discrete, read on, x label, well, basically the same stuff, frequency and spectrum. So I'm going to copy it. And title is discrete signal. So what we see now is that for discrete signal, our sampling frequency is now lower than it was here. So essentially, we now speak about mirroring the spectrum, not around 500 hertz, but around 100 hertz. But even so, at 100 hertz, we can conclude that this spectrum actually finished already, yes. So from that perspective, we can say that condition of Nyquist's theorem, that is sampling theorem, that you need to choose your sampling frequency of 200 to be at least double of whatever maximum frequency you have here is fulfilled, meaning that we expect it will be possible to perfectly reconstruct this signal back to its original form, from these red samples all the way into this blue line. And this should be possible perfectly. So let's see if it's so, if it's true, and if it happens by trying to do that. But before that, actually, it would make sense to check if spectrum changed or not. Well, that's actually possible if we kind of say zoom this fragment to also be in range of 200 hertz, like so. Now you can see that actually these two spectrums are the same, yes, except that for discrete version, here we see the replicated mirror copy, whereas for continuous, that is analog signal, it was simply decaying further and further, yes. Now, of course, this is also discrete signal with much higher frequency, but we just don't see it here. Yes, we consider that it's actually as analog signal. The shape of the spectrum itself didn't change. That's quite important. Yes, maybe some numerical values a little bit. No, they are not different because my scale is different on the vertical axis here. You see that maximum was 2. Here I didn't reach maximum of 2. But anyway, what we want to do now is to somehow ask MATLAB to do this stuff for us, to put them on the same limits. Yes, that's actually possible, and it's not difficult at all if you specify the limit after the plot you want to change. So this plot is automatic. Well, considering these two limits, 200 for the lower plot is smaller than the upper one. So we will always limit the first picture, yes, to 200. Not, and we will not change this one, well, because no point. We can specify, okay, limit is from 0 to 200, but it already is in this limit. So let's specify this limit for the first plot. Here, specify a matching frequency limits to be in line with plot 2. That's called command xlim. So we specify x-axis limits, and there you need to specify two numbers, minimum and maximum, like 0 and f discrete sample, f discrete sample frequency, yes. The same way you can also limit y-axis if you want to, yes. You can either use specific numbers, hard-coded values, or variables here. So after we do this, now it's actually completely precisely matches, yes? So we can see that it's exactly the same for this part, and for this part, it's a mirrored copy that is result of sampling operation, yes? So we consider that as unsampled, and this is the sampled version of it. So with that in mind, we can now verify that first of all, sampling actually preserved the original spectrum. There was no corruption to it. Second, judging from this fact, we can then consider that it is possible to reconstruct it ideally. So let's see if that's true by actually trying to do this. That's going to be task number 3, I believe, yes? Yes, we will use a built-in, no, that was actually task 3 to calculate FFT. Yes, so just a minute. Yes, that was task 3, so now we have task 4. So I'm going to leave the title action in task 3. Task 4, reconstruct sampled signal and compare with original analog signal. So in this exercise part, it will make sense to display two signals on the same picture, so that if they match, they are actually going to be overlapping with each other. If they are not matching each other, then you will see easily where they are different. Now, That's actually quite simple task because I have actually said that we will use a specific function called resample to do so. Now, in lectures, we did discuss that the reconstruction is performed by connecting these samples, or rather than connecting, let's say, maybe better, replacing them, um, let's say blue color, with a scene x versus x type function that goes through zeros for any adjacent samples, like so. And that's exactly what this command resample does. It resamples, that replaces each of these samples with this function, adds everything together, and then you make sampling with a new frequency that you specify. So kind of we could do the same resampling also to make sampled version by specifying sampling ratio like you downsample. But instead of that, we actually, what we do here is we upsample the signal back to its original ratio. Yes. So that command belongs to some package. Let's check if it's here actually. Resample. Yes, it's here. Yeah. So basically, it shows some examples, and notation is quite simple. Yes. Blah 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 blah. So first, you specify the signal which you want to resample, and then the ratio of P and Q with two numbers. P shows the if I'm not mistaken, the upsample ratio, and Q shows the downsample rate. For example, you could upsample it 5 times and downsample 1 time. Yes, so that's total ratio of upsampling by 5. Or you could specify P10 and Q2. That's also going to be a ratio of 10 divided by 2, 5, or 15 and 3, etc., etc. Yes, it's not going to make much change here. So what we are going to do here is to upsample it by ns, and that's it. So let's call this signal SR, recovered, by running resample. The signal we want to resample is S discrete. The upsample ratio is ns, the downsample ratio is 1. So for example, if we want to downsample signal to make sampled version, we would change these numbers. Yes, so it would be the same. Well, let me actually go here. So the same operation as this line can be actually done by resample S1 and NS. And that's going to be the same as D. So this can also be done this way by using this built-in function. But that's overkill, honestly. All that you have to do is just skip some points and not replace every point with scene of X versus X, then take samples from there and blah, blah, blah. That's just like shooting birds with a huge cannon, yes? Here, however, we actually need to fill in missing points that we don't have, yes? So that's why we use resample command. Well, finally, there is the figure 3. Let's display results. We don't need to specify any additional time vectors because we are back to our original time vector t. So we now display two plots. Plot of the original signal, that's going to be original signal, then hold on, plot of t and s recovered, hold off the resampled or recovered signal. We don't do subplots here because we want to have them on the same picture, yes, to be able to say if they are same or not. But before actually drawing that, I'm going to add some labels. X label, that's going to be time t, and Y label is going to be a signal. Also, I'm going to add a legend saying that the first signal is original, the second signal is reconstructed. That should take care of everything, yes. So here we have our original signal and sampled version. Now we'll see how the original and reconstructed signal look like. Now I will see if I want to have, I suppose I actually do want to have this one as line width 2, and this one will be then seen as this line on top of this line. Because if I don't specify line width here, they will merge into one single line and you will not be able to understand. Maybe one of the lines didn't draw properly. Now this way, one line is going to be thicker than other and you will clearly see that they are matching each other. So let's run it. And here we actually see that there is some mismatch here. Yes, we can clearly see that it's not perfect at the beginning. I need to switch to zoom, yes. See how here it's actually slightly changing, whereas here it, well, almost goes through this line. Well, that's some limitation of the resample function because it's not exactly working as optimally as I described. It's somewhat practical limited a little bit, which leads to some effects at the beginning of the signal and the end of the signal. That's where you actually see some difference. Yes? Whereas in the middle of the signal, there is not much of this difference. Let me make this one like a red color. Well, actually, I'm going to make this line width 2 also, and red dashed line. So not a solid line, but a dashed line, or stripped, maybe like that, to see it better. No, it's not dashed, sorry. So I need to have strip, like so. Now, actually, it's easier to see where it matches and where it does not, yes? Well, in general, considering the limitations of our resample function, which we use because, well, it's ready to use and we don't have to hassle with accurate approximation, we can say that this actually gets the job done. And the recovery, although not perfectly possible, not perfectly done, but that's just because of our method we use, not like it's like theoretically impossible. No, theoretically it's possible to be recovered, but we use the specific algorithm that just doesn't do so at the beginning and at the end of the signal. In the middle, though, it's almost perfect, yes, with some small computational error caused by FFT and so on, yes. So we see that actually recovery is possible, and that was concluded also from this spectrum. Now, also I'm going to add grid on. Let's see the final tasks. The final task is to change downsampling from 5 to 10 and then to 20 to see what happens then. So what that means is that we are going to skip now not 5 samples, not 4 samples, but 9. Effectively, that means that this picture will now miss one extra sample in between. So we will have this sample, then this will be gone, this will be gone, and so forth. So we will have half of these samples only. So let's go back to the code, specify 10, and run it. So see, now we have a half of the samples left, and recovery is now starting to show some problems. Well, why that happened? That happens because the spectrum-wise, if we see the spectrums here, yes, you can see that actually we now have something like a aliasing effect, because these two spectrums no longer match perfectly, yes? Why is that? Well, that's because our sampling frequency is 100, which is supposed to be twice as a maximum frequency in this analog signal. But in analog signal, we can see that maximum frequency is something around 70 or so, not 50, because at 50 we clearly see here something happens still, yes? And that's going to be mirrored all the way up to this main spectrum, corrupting it. If your spectrum of signal is corrupted, the signal then changes its shape as well, which leads to irreversible damage. Yes, and when we try to recover it, you see that it's not working. That's only, yes, I can actually copy this. Can I? Copy figure. Then let's open MATLAB, Paint. Well, no, not like this. Well, then I'm going to use snipping tool. So what I'm speaking here about is that this part of the spectrum, so the choice of sampling frequency of 100 implies that outside of this band there is nothing left, but you can see clearly that there is still something. So that something was actually adding on top of your existing sample. So this sample adds to this sample, making it bigger. This sample adds to this sample, and so forth. And that corrupted the spectrum a little bit. Not much, because in general, we can still see that they are, well, maybe not exactly same, yes, but at least similar, yes. If we kind of like try to put them one on top of another, transparent selection, then you will see that there are some differences. They are not the same anymore. Yes, and because of that, the perfect reconstruction theoretically even is no longer possible. Yes, but we still get quite a good approximation of it, which might be enough for us if we say work with an audio signal with human speech, and our ears will just not feel any difference. Now, what we do further is increase this downsampling even further, meaning that now we are going to skip even more samples in between. So we'll have this sample and then this sample, and this will be gone. So everything like this shape will not be saved by these two samples. What happens then is even further degradation of the system. Yes, see, now we have this definitely insufficient sampling frequency. We do miss a lot of details when we take readings of the signal and keep only red ones. Because you need to realize that these red samples are the only thing that is left. You lose this blue line and you only work with these red samples. And you hope to be able to recover them. But that's not going to happen because the spectrums overlap too much. Yes, at 25, which is half of this 50 sampling frequency, and after that there is significant spectrum components that creates huge distortions. Here you can see that it reaches value 2. Here it was not exactly 2, it was below 2. Now it's around 2, yes? Just like this value. So that's again because same stuff happens, yes? Let me another snip, copy, paste. So basically, again, that's the same stuff. We limited the spectrum to here, but that's not true. That's actually there is something left here, yes? And all that is left here is going to, well, how they say, create a layers to these components. So this one goes here, and this one goes here. That's why this component has increased a little bit, yes? Whereas this component was increased by this number. So that was much huger and almost now the same here, yes? So that's actually called aliasing effect. That's what we observed when we seen this rotating wheel in different direction. That's an equivalent. There was a sampling done by a camera, like number of frames per second. Here is like a number of readings from your function. And if we have a valid sampling time interval like 5, then everything is fine. What I need to tell you is that I generated your random signals and they originally were not finishing at 100, and they were actually going all the way up to 500, and there was constantly a spectrum. So because of that, I created a filter to filter so that everything outside of 100 is gone. Yes? So that means if you really want to lower your sampling ratio, you have to filter those components out first and then do sampling. Well, that's story for another time though. For today, this practical exercise is concluded. If you have any questions, don't hesitate to ask. If something is not working, let me know and we'll try what is missing in your code. This video record will be available in the order system to match it if you maybe missed some parts. Yes, or I was too fast. And then accordingly, as I said, the deadline for submitting risk reports is the end of semester. So then thank you